So it's now 5 minutes past 10. I would suggest to start with today's webinar on our Open Innovation Photonics pilot line and our voucher call to help SMEs to get their PICs. So we've got a strong program for today. I think all of you has received the agenda for today. And I would suggest to start with Dr. Victor Dolores Calzadilla from the Technical University in Eindhoven for the welcome and the introduction of our today's webinar. So please, Victor, the floor is yours.
Yeah, thank you, Dirk. Well, I will start with an introduction. Welcome, everyone. And then my colleagues will continue with the different parts of the pilot line, namely front end and back end. I see that there are not too many people connected. Hopefully more arrive soon. And in any case, well, it's an opportunity for the ones that are participating to ask a lot of questions and get answers. So I will start with an introduction about the project. I am well, the coordinator of the project, and I'm sitting at the Technical University of Eindhoven. This is the consortium for the Open Innovation Photonics program that we have. It's a combination of research institutions with companies that are equipment suppliers, companies that are developing applications, and companies that have services in place like Smart Photonics, Tyndall, or Vrije Universiteit Brussels. They have different type of roles of services, and also clusters, cluster organizations that are helping to disseminate with business development, and to help also doing roadmaps of where this, let's say, emerging industry is going and how to join synergies together. Now, the targets of this Open Innovation Program are these three, I would say, in short. It's to contribute in increasing maturity and scaling of open access indium phosphide platforms, mainly the one of Smart Photonics. Then provide technology support to SMEs that have a first prototype, and they are looking to improve the maturity of their product, and we try to do it with an open, as open as possible collaboration where everybody wins. And then last but not least, more in the midterm, what we're trying to do is to establish an open innovation environment where researchers, founders, equipment manufacturers, and application developers can collaborate ideally in the same laboratory, in the same lab, in the same clean room infrastructure, and in the same way as it was done in electronics in the 80s, where big organizations establish an open innovation, and they work with several foundries, and they are able to share risk and cost of developing this type of technology that is more and more expensive with the years. Now I want to start also with this technical slide on the generic photonic integration, which is the kind of philosophy behind of photonic integration, at least to try to avoid a verticalization, let's say, of the ecosystem. Then by developing generic components, generic platforms, it's possible to offer, let's say, this technology to more applications. So more fields, more sectors can benefit from having application-specific photonic integrated circuit. In indium phosphide particularly, we are able to do many types of devices. So I would say classic passive components like splitters, reflectors, polarization handling elements, etc. But also more elaborated components like optical amplifiers, different types of lasers, different types of modulators, not only phase, but also amplitude modulators, etc. So that's, I would say, one. This is after the success of electronics, to develop basic building blocks. We are also developing this type of basic and more complex building blocks. What you see here is different cross sections of waveguide components. yeah, from amplifiers, modulators, and the passives as well. To be fair, these are our, let's say, classical images, but they are about, I think most of them about 10 years old. That means that by now, the quality of those, you know, the edge surfaces and the position of metal, etc., is much better. The development cycle of photonic ICs is displayed in this screen. Well, everything starts with the application needs, and then you can start while talking to the people that can do the design, then the fabrication of your PIC via multi-project wafer runs, for example, and then that will go to packaging and generating a product. In these years, particularly, we see a bit of a gap in these steps, in these phases. You know, we're going from fabrication to packaging, or from packaging to products. Those are not well supported by the ecosystem yet, and that's where the OIP4NWE project enters. So we are basically, our SME support is focusing in these parts, in these interfaces, and we want to support SMEs with an action that we have, that we just launched. It's called the Innovation Support Fund, and there we want to provide services. You know, you provide in-kind services to the SMEs. Where do we situate the OIP4NWE project in the TRL scale? Well, in the yellow blocks you will see here. We are looking for companies that have a first prototype, you know, that have done maybe a first iteration cycle. They have one prototype, and now they are looking to continue development, to do a next iteration. And most importantly, you know, they want to do it with a set of companies that can have a path to manufacturing. So companies that are working in a specific approach that can offer in the very soon manufacturing of high volumes. So that's what we are offering, to work together in this regime. This slide situates very well the contributions of OIP. Well, as you can imagine, the PIC industry is going through a continuous reinforcement cycle in all aspects, not only, I mean, fabrications or backend, but also beyond technical capabilities. It's a continuous reinforcement cycle, and particularly OIP project is contributing to these two pillars. So to further develop the photonics ecosystem, we have several actions there, and also accelerating the scale of processes. So we also have technical lines where we are looking to scaling the processes, the fabrication to a larger substrate sizes, for example. And yeah, so we have several actions, some more in the midterm, but in the very short term, what we have as a mission is to support SMEs. Now, this slide is about well, the design of manufacture of PICs can be done thanks to process design kits. That the concept was borrowed also from electronics, and it works pretty well in photonics. It needs improvement, but a lot of partners are working on that. And via process design kits, you can design your design house can design an ASPIC. What the folder provides is the design manual and the functional building blocks, let's say, to put them in the design. And in the OIP project, we are also working to have in the midterm improvements in epitaxy, yield, stability of the process. So that's one action we are doing, mainly in cooperation between the TUI, Smart Photonics, and Axtron. We also have partners that offer packaging services and technologies. This is a very nice picture from Tyndall. And they're obviously able to offer different types of carriers, interposers, and interconnection technologies. And particularly in the project, we are looking at the ones that are in yellow circles here. So at the let's say optical connections with the fibers, so improving tolerances, for example, also with by use of micro optics for beam shaping or also for increased alignment tolerance. Flip chip technologies, high-speed interposers, thermal management. So these are things that Tyndall is improving in their capabilities, and also other type of new, let's say new technologies for interconnection, like this technology from BUV, where they are fabricating different types of, well, micro optics or freeform optics for microfluidics or for better coupling, very small modes, high contrast modes in indium phosphide to optical fibers. And this is my last slide, I believe. So as I said, we are launching this. We have launched this Innovation Support Fund, and now we have a call that is open for about 3 months. And you will hear more in the presentation, later presentation. But the idea here is that we are able to offer vouchers to SMEs that have a first prototype, and they are looking to do a next iteration. And then at the end, what we want to give them, we want to support them with the development and be able to deliver a series of package chips for their application. So if it is granted, well, then it's going normally through this path. So Smart Photonics will fabricate the PICs. BUV is able to design external optics for the applications that need that, and Tyndall can do the packaging. So more about this will be presented later, and you will have the chance to ask questions if you have. That's it from my side. Dirk?
So thank you, Victor,
for
the introduction. And as Victor always said, we've got 3 partners, and we want to give them the chance now to give you more information about our activities. And I want to please Nazanin Shafi from Smart Photonics to continue and to present the manufacturing of the integrated, the photonic integrated circuits. So please, Nazanin.
Perfect. Thank you. Thank you very much for the introduction, Dirk. Let me start by trying to share my screen first. Let me know if you see my screen.
Mm-hmm. Sorry.
Okay, let me know what you'd like me to start. Oops.
No problem. Yeah, now we see it.
Works.
Works. Okay, perfect. So thanks very much for having me. It's a great pleasure to be here in this virtual room with all of you and the panelists that we have here today. And I always like to talk about the manufacturing aspect of PICs. But as Victor introduced, I want to take a step back, and before talking about photonics, I want to talk about integration, and specifically for electronics, because the impact of the integration of circuits that we see today and over the last number of decades has been purely because of integration. In fact, the biggest companies that we see today in the world wouldn't have existed without the integration. So now when you think about it, it was just 60 years ago when the first monolithic ICs were invented. And perhaps 30, 40 years ago, people thought it was crazy to have people of the future to walk around with a little computer in their pocket. The phones that we now use as a phone and a smartphone, an email and internet access. So now, using the same logic and the trend that we've seen in the revolution and evolution of electronics, we see the same for photonic integration. We expect it to do the same. We expect it to, again, revolutionize our world today. And we know not only will it bring in, but it will also enable a whole wealth of applications. PICs will become the principal engine of many of our future products. And the future of the sci-fi movies that you see it may very well be just around the corner. There we go. So what areas are we able to address and help enable? Well, some of the main areas that you see, high-tech, healthcare, aviation, automotive, energy, these I would generally categorize under the sensing application. And then you've got the telecom and the DATACOM that falls under the communication. Again, I'll talk a little bit more on these applications, but before I keep you waiting too long, I want to go over the outline of what I'll be talking about today. So first, I'd like to talk about the company, Smart Photonics. Then I'll go over the PICs technology, the application, the platform, and look a little bit more detailed closely at the generic platform, some of the building blocks I'll scan quickly over, and some of the devices that I'm able to share. And then I will open the floor for any questions that there may be. So, intro into Smart. Maybe I'll start with a very quick intro on myself. I've spent most of my career on high-tech manufacturing, and I've made parts in telecom, as you see the MEMS mirror. I've made chips, the Fresnel zones for X-ray manufacturing, and on the health side, devices that are used for surgical purposes, and in fact also implants. And you know, I'm excited that I can take some of this experience and bring it into the new platform on indium phosphide technology. Now, talking about our company, we're an independent pure play foundry, and we manufacture photonics component on indium phosphide wafers. As a pure play, we obviously are very focused, 100% focused on manufacturing of parts for our customers because we don't make any other products for ourselves. So in essence, we're not competing with our customers. There is no conflict of interest, and that's not necessarily the case with all foundries. Now, Smart has a fairly long history in photonics. We come from Philips and also Technical University of Eindhoven. So we've got the main two strong foundations, I would say, on the main two pillars being research and manufacturing. And we take that and help our customers to develop products at the very early stage. So that is the proof of concept, feasibility, if you will. And then we take them along the journey to prototyping and manufacturing, high volume manufacturing. Now, something I'd like to maybe point to is just with the recent round of funding that we've received, we've done a lot over the last year. I'm kind of losing track of how many tools we've been able to introduce over this time and how many are coming on board and getting qualified, and same with our team getting expanded. And all this is to make sure that we're able to support the 10 times capacity increase that we've targeted. So we're very excited about that. Now, I'd like to transition over to the PICs technology and applications. Again, in terms of the applications, this is some of what I've introduced. Obviously not all the markets are being presented here. And maybe I'll talk very briefly about a few. Perhaps DATACOM is an appropriate one to talk about. When you think about the DATACOM, it's no surprise that our society is very hungry for data. We've seen that a lot more over the last year. But not only are we seeing that we're demanding more data, we're also asking it to be delivered to us much faster. And this is getting us to a point that the industry is simply not able to address the demands that is being asked by the market. In fact, they're behind what the market is asking them to be providing. So, you know, it suffices to say that the transceiver market is just booming. And you know, when you think about these transceivers, they're just little devices that allow the communication to happen. So there's a lot of restrictions and performance requirements that is demanded of them. You need to meet certain performance spec, as I said. Part of it is the power consumption, there is the size restriction, and on top of all this, there is the cost requirement that it needs to be meeting. So, you know, these are, again, very specialized devices because of the technology that we're able to provide. So specifically on this, maybe worthwhile to say that, they use DWDM technology. So it's division multiplexing, dense wavelength division multiplexing. And essentially by using different wavelengths of light, they're able to route the data differently and make it more efficient, more flexible, more cost effective, not only to build, but also to own and operate when you're comparing it to various other ways of connecting the communication. So maybe I won't spend a whole lot more time, but nice to kind of see how the market is also being attracted towards automotive, biometrics, security, and some of the other industrial applications, robotics. Again, on the sensing side, slightly different side of looking at it. We're looking at here a PICs readout unit. Sorry, there we go. A PICs readout unit. And this is used for temperature, strain, and pressure measurement. So there we go. Now I'd like to transition over to the technology and platform. I realize it's a short talk, and I'm just kind of trying to briefly give an overview of some of the things that's probably going to be able to kind of put the whole concept in place. In terms of the PICs technology and the comparisons, well, there are the different platforms. There is silicon, there is silicon phosphide, there is indium phosphide, silicon, and silicon nitride platform that can be offered. But it all really comes down to the system requirements. What does the system require? What are the building blocks that need to be used to create that device and system? And when you look at the performance, the green dots that I have is showcasing the performance. If, for instance, all you're requiring for your system is a passive component, well, it's probably a better choice to go with the silicon nitride platform. But if you do require some active components like lasers, like amplifiers, well, as you see, the other two platforms simply are not able to offer that, right? So here's when the main advantage that indium phosphide platform offers really can get highlighted because of the monolithic integration that it can have. It does bring a lot of advantages in terms of the performance, final performance of the device. Looking at some of the components that we can have, obviously for the passives, you can make it on all the three different platforms. But for switches and modulators, now you're limited to only two of these platforms, silicon and indium phosphide. And as I said, to make the active components, the lasers, really indium phosphide is the platform of choice. And if you are requiring a lot of these components, the integration makes it a lot more seamless because all of these components are being put in place simply by the processing of the wafers, and there's no additional later requirements for assembly of these components. I want to take a step back and again look as to why the market is transitioning towards indium phosphide. Here you're seeing the indium phosphide photonics market, particularly on the DATACOM section on the transceivers. So, the main thing is, worth talking about is that the telecom and DATACOM industries put a lot of really tight requirements on the devices. And again, obviously, they are very much gravitated towards this platform. But when you think about the established photonic market, now that we've got this really mature platform, there is huge opportunities for a lot more markets, as I pointed to the fiber sensor readout units, medical, metrology, and many other applications that still can be investigated. But again, I think the graph really speaks for itself and making a very strong case for making use of indium phosphide compared to some of the other technologies available for making photonic components. Oops. Now, cost is an interesting topic to talk about because quite often I hear customers asking and comparing the cost of a silicon versus indium phosphide. Yes, it's absolutely true that indium phosphide substrate does cost more compared to silicon. But when you look at the overall cost of a device, about 80% of the cost is on packaging, assembly, and testing. So you're essentially looking at less than 20% of it being the cost of wafer manufacturing. And of this 20%, the cost of the substrate is really quite insignificant, right? So this is a good case to talk about because you're looking at, again, specifically on the transceiver DATACOM market, but you're looking at the breakdown of cost on a DWDM. This happens to be a 10G SFP+, and down below you're seeing a high-end coherent transceiver. So what I've got on the y-axis is the currency that's been normalized with respect to the de facto industry standards. So you're looking at roughly cost being cut down by a factor of 4 when you're bringing the manufacturing to an indium phosphide platform. So I think this is as much as I'll talk about on the cost front. Now moving towards the generic platform, building blocks, and some of the devices. Well, first question, well, why are we talking about this generic integration platform? Why is it such a big deal? And why does it even matter? So, we talked about how electronics managed to revolutionize the world by the integration. This is really what we mean when we're talking about a generic integration platform. So we're providing a platform that is already optimized. You're enabling the manufacturing of high-performing devices on it. It's an easy and versatile platform, as I'll show you down to the road, like a few slides down, on how easy it is to bring in some of the components. And essentially because the work has been done to develop this, the cost is very low for the customer. They've got processes that are standardized. Essentially, they're well understood. Our tolerances are very well known. So because of all this, we're able to scale and make the component manufacturable at a fairly rapid time for the customer. And how do we do it? Again, Victor mentioned briefly, we use the PDKs, the process design kits. So again, we essentially have a set of files, models, to be able to communicate the fabrication of these components and be able to have that communication with the designers. And the thing that I want to stress on this slide is that we make these components on our PDK as the functional level. So these components are functionally usable. So maybe a good example would be when you were to drop a wire on an electronic simulation platform. Doesn't matter how long or short your wire is, the wire is a wire. Whereas here, even though you see the waveguide being represented by, again, a simple wire or a simple line, now it matters because the length of it will speak to the phase as an important parameter of light, right? So you can't just put any size of or length of the waveguide because you're essentially changing the performance of it. So the units, as a designer, the designer as they're using it, they're able to actually simulate the device that they make it. So again, it all leads to faster development of the devices and lower cost at the end for the customer. So we work with a number of state-of-the-art software tools. Again, with the use of the PDK, the design and the simulation, and laying out the design is fairly easy. And when all that has been done and approved, then we receive the same design, again, using the tools from the designers, and we manufacture it. I think maybe worth mentioning that we also provide, obviously, the design manual, and it's got the description of the functional building blocks as part of it. So the next number of slides I'll go through very quickly, just to showcase some of the components. Here you're looking at an electro-absorption modulator, but demonstrated bandwidth of more than 55 gigahertz. Again, we're adding additional components on our NPW platform, but we're always able to do custom design as well. Here you're looking at a phase modulator. This slide, you're seeing a DBR grating. The thing to take your attention to is the high yield of these components. We can make these components with fairly high reproducibility. The variation is fairly low. It's less than 1 nanometer across the whole range. And again, this is another component we have available on our PDK. And using this component, what you see here is you can make a laser with an output of about 10 milliwatt. Again, these are just very simple examples that I'm showing you just to showcase how you can use the building blocks to make devices. Another example of a mode lock laser. Here, when you look at these devices, you're looking at a 30 millimeter cavity. I think that's quite nice and impressive. This is used for a gas sensing application. Here, another mode lock laser. I'd like to bring your attention to the sharp peak of this graph. Another example, this is for a gyroscope system. And here you're seeing a low line width laser, a ring resonator, again using simple building blocks on our PDK. I think the one slide worth spending a little bit more time on is this one. What you see here is a very small footprint, dense integration of a PIC. You're looking at 6 Mach center modulator, you're looking at 6 tunable laser, and again, all this is available on our NPW platform. And with this, you can get a really powerful device. You can get a single chip that can transmit over 100 gigabit per second. And this is truly the power of a generic platform. Without a whole or any modification, we can make something like this very quickly and easily. Another great example is this one, another very high performing device. Again, low line width, full band tunable. This one we're showcasing on the left, I'm showing you the simulation and the prototype as after we manufactured it on the right. This happens to be on the C band. Again, all this can be easily done on O band that we're also developing. This is a great slide to talk about our process capability. I think I may have mentioned that we use a RF litho scanner, and one thing to note is that it can create features to with very low dimensions, right? So you can get less than 100 nanometer features. And not only that, you can get very high throughputs of wafers at such small features, which is really quite impressive and quite powerful. Because in this case, specifically for the AWGs, the gap here makes a difference for the performance. So if you were to compare standard traditional litho tool versus what we use, you could easily be looking at 5 times reduction of the losses, which is huge when it comes to the performance of the device. I hope that that's given you a nice flavor of what we have on our platform. I'd like to kind of quickly move on to wrap up and give you a summary as to why to use indium phosphide. So here I've got 6 reasons why you should be using or you want to be using indium phosphide. But if I want for you to walk away with only 2 reasons, I think the first one would be that indium phosphide does enable a higher performing chip because of its ability to do monolithic integration. And the second is that with the higher performance, you're also paying less. So again, cost is a very, very major issue, and for a good reason. So these 2 reasons would be why I would suggest indium phosphide being a preferred choice in a platform. Now, what SMART does, obviously, as I said, we help our customers do the development, but also have for our customers to go from the development all the way to the production. So we do prototyping, optimization of the wafers, and piloting and commercialization. So we pass through certain gates for the different projects. You can check out our MPW on our website, the schedule, when the designs are due. And again, that's not all. If there is any customization, we're obviously able to also do it. And otherwise, if the timing doesn't work, you can also have the dedicated runs. And with the Innovation Support Fund that you'll hear about shortly, I think that would be a great help to be able to make this transition easier. And with that, I'd like to open up the floor for any questions, if there may be any.
Thank you very much, Nazanin. Sorry, there's someone wanted to say something. No? Yes, Lasco?
Hello, Nazanin. Thank you for the presentation. I was wondering about the direction of development of SMART in the future. Do you see SMART more stabilizing the single platform and expanding the design manual, or perhaps diversifying platform to be optimized for different applications?
By application, do you mean different technologies, different markets, or do you mean different parts of the bandwidth that we can make use of, like C-band and O-band I referred to?
Different fabrication process tuned to an application. So branching the single fabrication to several.
So we're constantly developing our platform and optimizing it. We're adding components, we're optimizing the performance of individual components. But the thing to stress is that all these components, you can, by how you make use of it, by which components you bring in, you can make it to address a different need created for a different application, for a different market. Perhaps Victor can shed light on some of the different applications here as well. But you don't need, we are not focusing on a market, if that's what your question is. We're focusing on optimizing our platform and making it, maybe adding components, maybe, you know, right now we're focusing on 1550 platform. That's a very ideal range of bandwidth for customers to develop their products, but we're also expanding that. So it's not just the C-band, we're also creating the O-band that we have not had before. So before we would have done that on custom cases, but now we're opening it again as just a generic platform for any customer to just use it for any kind of application that they're looking for. You know, like if you think about sensing, you can think about, you know, lighter automotive, you can think about agriculture. I didn't refer to that. Again, medical falls onto that, right? So you can use different components, right? I don't know if I answered your question or if you had a selection.
You did. Thank you.
Okay.
Thank you. There's another question, or otherwise there's none. You can use anytime our chat function to write there your questions in it, and we will collect them and discuss them after all the presentations. So feel free to use it, that you don't have to keep in mind your question up to the end. So, and thank you, Nazanin, again for your presentation. Now, after the first step, we've got our chip. And now the question is, if you got not a free space optics, you need to connect them to a fiber. And that's the second part. And I welcome Jürgen van Erps from the Vrije Universiteit of Brussels with this presentation about optical interfacing of PICs with the outside world. So please, Jürgen, the floor is yours.
Very much, Dirk. Can you also see my screen?
Yes.
Let's try to put it full screen like this. Okay, good morning, everybody. So indeed, part 2 of the pilot line would be, is there a need to foresee some external optics or some coupling units to interface the PIC with the outside world? We at BPhots are located at the, we are basically at the Photonics campus of the Vrije Universiteit Brussel, located in Gooik in Belgium. More information can be found at bphot.org. And basically what we try to do at BPhot is to set up a full supply chain of technologies that allow you to go from modeling and design over prototyping and manufacturing, metrology and quality control, as well as proof of concept demonstration for mainly freeform optics, ranging from micro optics to really macro scale optics. And so we address basically the full chain there. Now, what I would like to go through with you briefly in my presentation is the following. First of all, looking at the fiber-to-PIC coupling. Victor already showed one of the images of mode conversion down-tapered fibers. So I will give you some more information about the developments we've been doing on those down-tapered fibers within this OIP4NWE project. Then, of course, we can do mode conversion up-tapers as well if expanded beam connections are required. We also have some capabilities in terms of controlled thermal core expansion of specialty ultra-high numerical aperture fibers. So these three options might be useful for interfacing the fiber to the PIC. The second item is PIC-to-free space coupling using external optics. The word optics is missing there. So basically, two options are available there. We can do refractive optics or we can do diffractive optical elements. So I will briefly introduce the capabilities we have on both of those. And finally, our manufacturing pilot line can also be used for microfluidics fabrication and this can then be used for PIC-based sensing applications. So let's go through them in a little bit more detail. So interfacing fibers and photonic integrated circuits. You've seen the picture on the right in Victor's presentation already. It's a picture that comes from the PICSAP website and is courtesy of Tyndall. As you can see, you have to interface the PIC, or in this case, the indium phosphide PIC, with the outside world, in many cases through optical fibers, optical fiber arrays, or through micro-optics components. One of the great challenges in interfacing the PIC with fibers when using edge coupling is the fact that you have a large dimensional mismatch between the size of the single mode fiber core as compared to the waveguide on the device. So you have, as an example, on the bottom left, you see a mode field diameter of a standard single mode fiber, which is on the order of 10 micrometers. And on the right side, you see an example of an SOI waveguide. So it's just an example where the mode field diameter is on the order of half a micron. So you see that you have a 20 times smaller mode field diameter on the PIC embedded waveguide than you do on the fiber. So it's clear that if you just position the fiber in front of this waveguide, you will not get a good coupling efficiency. You will have huge losses. So what are the other possibilities in coupling the fiber to the chip? Well, you could use grating couplers. Then you do some kind of out of plane coupling. So in the first image on the top left, you see the SMF coupled through a grating coupler, where the SMF is at a near vertical position to interface with the PIC. But in terms of assembly and packaging, in many cases, you would prefer an edge coupling over a grating coupling scheme. And typically one would use a lensed single mode fiber for that purpose. So then you typically have a mode conversion structure on the PIC, and you apply a process to the glass fiber such that the tip of the fiber is forming a lens that, of course, needs to be used in a kind of free space setup. So you need some distance between the PIC and the apex of the lensed fiber. An alternative is to use physical contact-based solutions. They are a little bit more robust in terms of packaging, of course, because you then can actively butt couple the fiber to the chip, and you can also apply epoxies or index matching materials to reduce the reflections at the interface between the two. This is an example of such an ultra-high numerical aperture fiber, which has a pretty small core that can then be thermally expanded to match the mode field size of a standard single mode fiber of 10 micron. What we have been developing within the framework of this Interreg project is actually a mode conversion structure to be printed on top of a single mode fiber. So you see the schematic illustration at the bottom, where you see that my laser pointer's too pointy. So where you see that you have the standard single mode fiber, and on top of the core, a structure is written that gradually reduces the mode size of the fundamental mode in the waveguide. So this allows you to tailor the output profile here, or the output size of the mode, to the mode field size of the waveguide on the chip, and potentially allows you to save some real estate on the PIC, which would normally be used for mode conversion structures like used with lensed fibers and even with the ultra-high numerical aperture fiber. Now let's take a brief look into the design. I won't go too much in detail here, but a first approach is to use a step index design, which means that you have a polymer taper on top of the fiber with an air cladding around it. So as mentioned before, we have here a gradually reducing diameter taper of a certain input diameter and a certain output diameter, and you basically design the input diameters to have a maximal coupling between the single mode fiber in glass and then the polymer down taper structures. Turns out that this optimal mode overlap is achieved for an input diameter of 15.1 micron. This is on the input diameters, and by performing some mode simulations, some eigenmode expansion solvers are used for that, you can actually model the propagation of the fundamental mode along the length of this taper, and you see that in the graph here on the bottom left of the slide. And what we did is actually fabricate several of these down tapers with output diameters ranging from 1 to 7 micron, with a length of 250 micrometers, such that we can address or let's say match the mode field of several different waveguides embedded on photonic integrated circuits. I will show the experimental coupling results in a second. The idea is, of course, to fabricate the structures. So what we see on the right here is the fabricated down taper with a linear profile, a length of 250 micron, as mentioned. And what you can also see is that we included here a base plate, which is required to ensure a good adhesion of the taper to the glass fiber, together with this base plate, which we designed such that it has minimal influence on the optical performance. And we also apply a chemical cyanization process to functionalize the surface of the glass to create a better chemical bond to the polymer structure to be dispensed on top of it. This is on a single mode fiber of 125 micron diameter, but we can of course also make those structures on top of fibers embedded in glass blocks, in V-grooves. So you see that the two images, SEM images here in the middle. And finally, we can also adapt the shape of the taper in such a way that we have a non-linear taper profile, and on the figure here on the bottom, we applied a parabolic shaped taper, which allows us to reduce the length that is required to get to the same mode field size as with a linear taper. So the optical performance of the taper here on the top, the linear taper with a length of 250, is the same as the optical performance of this non-linear taper with a length of only 63 microns. So that's an alternative that can be used. And in terms of total fabrication time, printing such a taper takes about 5 minutes. So the other processes can actually be used in parallel over multiple devices. So if you have, for example, an array of fibers on which you want to print those tapers, then you just have to count the printing time of the taper itself. As an alternative for the air-cladded tapers that I just introduced, we further elaborated the concept towards a microstructured taper design. The idea is here to work on the principle of microstructured optical fibers, where you have air holes in a certain pattern distributed around the solid core, in such a way that you can tailor the guiding properties of these fibers. So we applied these concepts to our down tapers, where again we have a certain size of these air holes in the input side of the taper. And then we have these air holes running along a straight line and getting closer together and to a certain distribution at the output side, where we have again then a certain targeted mode field diameter. In this case, we targeted here a mode field diameter of 4 micron. And what you can see also on the picture here on the bottom left is that these microstructured down tapers allow a perfectly adiabatic mode field conversion, which is a little bit better than this than the mode field propagation that you have in case of the step index cladding, just because you have the possibility of exciting higher order modes in the step index cladding, which you don't have in this microstructured taper design. Yeah, so here you see the parameters that we've been using in terms of the size of the holes and in terms of the number of rings and the distance between the different rings. The taper length is still the same, 250 micron. So, and as mentioned, you have in this case a perfectly adiabatic conversion. You don't have the need for applying a cladding material if you would like to do so. And again, the contact surface of this structure is pretty much larger than what we had for the step index taper. So maybe you could also omit the base at the bottom of the component. And you can also tailor the functionality of these microstructured tapers to, for example, have some birefringence functionality. And this is something that we would still like to investigate later on. The fabricated structures, you can see them on the right. And so here, of course, you see that the printing time is increased a little bit because you have more volume to be printed on top of the fiber. And you see here the openings at the bottom of the structure as well as on the top, because of course, these are the air channels that need to be fabricated along the taper. But in this case, the actual core of the taper is protected from the environment because you have these air holes around it, and it overall makes a more robust structure. The development time that is required for those structures is also increased as compared to the step index tapers, just because you have to make sure that you remove the material, the unexposed resist material from these channels that you end up with nice air holes. Then we did some coupling experiments to validate the concept, and actually we coupled from fiber, standard single mode fiber, to 5 different PIC platforms, ranging from the silicon nitride, and the indium phosphide platform. And so you see here the waveguide layouts that were present on the chips that we had available in the lab. And on the bottom here, you see how we performed our butt coupling experiments with these different versions of the taper that I showed. You have the linear step index taper, the non-linear step index taper, the microstructured taper, and as a reference measurement, we also did all of these measurements with the lensed fibers, which are typically used as state-of-the-art solutions for these coupling experiments. For the step index tapered fibers, what we did was, first of all, try to measure the mode field diameter with an infrared camera to see how large the target mode field diameter was. And as you can see, we were able to quite well define the output diameter of our linear tapers down to 2 micron, and this is basically the optical resolving limit of the system. So yeah, we cannot go beyond that. So we cannot check whether our 1 micron end taper is effectively 1 micron, because we were not able to characterize it there. But with all of these tapers, we did the connection to the 5 different PIC platforms that I showed before. And as you can see in the graph, you can for all of these measurements find an optimal point where you have the highest coupling efficiency with that particular platform. Specifically, if you look at the indium phosphide platform, you see that we have the best coupling loss per facet at a end tip diameter of 2 micron, which is then the diameter of choice if you want to couple two indium phosphide waveguides. Now, if you look at the values that were measured, you see here the comparison of the linear taper versus the length fiber. And as you can see, we have in 4 of the 5 cases a much better coupling efficiency or a lower coupling loss, whatever you like. And for the indium phosphide platform, the improvement was the highest, about 1.4 dB lower loss per facet. And then we also have a comparison of the linear versus the nonlinear taper. And as you can see, the nonlinear taper has an additional loss penalty of about 0.1 dB per facet. And so you can make the structure much smaller while having a minimal impact on the coupling loss. For the microstructured tapers, we repeated those measurements for 2 particular PIC devices in this case. And so again, you see here the coupling of the MOF taper and the coupling efficiency achieved with the step index down taper, and you see that the values are pretty much the same for both cases. So this shows that the concept is also valid in the microstructured version with that connotation that you have there a cladding material around your core incorporated, and that the structure gets a little bit more robust. So what we plan to do now is to investigate together with other partners within the OIP project. We plan to look at the potential of these devices in standard packaging processes. So because that's of course the next step. If you can do down tapers, you can of course also design up tapers. And so in this case, I just put a slide with some designs of up tapers where the mode field has been expanded. And so both on single fibers as well as on a glass block with V grooves, an array of 8 fibers in there where the structures are written on each of these cores, with again such a base plate to increase the contact surface between the polymer and the glass. On the right side, you see the microstructured version of the up taper, and on the bottom of the slide, you see the output mode field diameter. So the standard SMF1 is here on the right, so 10.4 micron, and the output mode field diameters of the beam expanded tapers are shown here for the step index and the microstructured one. In this case, we targeted around 20 micron mode field diameters in both cases. All right, the third approach is to use this ultra-high numerical aperture fiber, as I mentioned before, and where you typically have a specialty fiber which has a very small core, which more or less matches the waveguide mode field on the chip when using a mode converter on the chip. And you can apply a thermal heating process to let's say, make an adiabatic transition from the mode in the ultra-high numerical aperture fiber and expand it to match the one of the single mode fibers. Achieving a perfect adiabatic mode conversion there is not so straightforward. And we have been working a little bit on that process by making use of a CO2 laser-based splicing equipment to have a good control of the energy deposition to perform this expansion of the core. All right, the second part here is basically looking at free space coupling, so using refractive optics, refractive micro optics. And yeah, the time slot here doesn't allow me to go through all the details of the manufacturing capabilities that we have here, but there are 2 big things or 2 big messages that I need to give. First of all, we can do either a direct prototyping, or we could even look at scaling up production by looking towards replication processes. So in case you would want a low volume production, you would like to go to a process where you make a mold that can be used as a shim in either a micro injection molding process or a hot embossing process. And so both technologies we do have in-house. In this case, we would end up with a polymer material. We can also do direct fabrication in glass by grinding and ultra precision bonnet polishing. This is mostly for larger optics, so it's not so easy to apply these processes to really small micro optics where you have lenses on the order of a few hundred micron. But in theory, we could also go towards replication in glass, where you would then use a harder material for the mold manufacturing and apply then a glass press molding step, which allows us to go up to 800 degrees Celsius, such that we can also replicate the component in some types of glasses. And for direct prototyping, of course, we can use the 2-photon polymerization-based 3D nanoprinting that was also used for these down conversion and up conversion tapers. And we also have a femtosecond laser machining station that allows us to do micro-optics fabrication in glass. Typically, those structures, because there you basically change the glass parameters by exposing it to femtosecond laser pulses, and then you remove the exposed material by a chemical etching process. Typically, those surface roughnesses are not of the same quality than what can be achieved with the other manufacturing routes. But we are developing the process of applying a fluid jet polishing process after the femtosecond laser machining to smoothen the optical surfaces, but that's a process under development. So to illustrate a couple of examples, on the left side here, you see actually a mold fabricated with ultra precision diamond tooling. This is a 6-channel vision system where you have a top mold and a bottom mold with 6 different freeform optical components. And then on the bottom here, you see the replicated version where you have on each side of a polymer sample, you have these lenses embossed. For, in this case, a particular distance estimation vision application. This is about the size of a full frame sensor, so 36 by 24 millimeter in total. And on the right, you see micro-optical components that were directly prototyped with 2-photon polymerization. So here you see 100% fill factor, square footprint micro lenses. And on the bottom side, you see some micro reflector array where the scale bar here is 50 micron, the scale bar here is 30 micron, and so you can see that you can make extremely small micro optical devices with 2PP printing process as well. We can also make some diffractive structures. So in the example here, we have targeted a 1-to-7 fan out of a single beam. This is for an application where we wanted to couple one single mode fiber to a multi-core fiber with 7 cores at a certain position with respect to one another. So we can do the design of the diffractive element that performs this 1-to-7 fan out, and then we can also use 2-photon polymerization to print the diffractive optical element. And in this case, we have a 4-level structure, and you have a binary height profile here. But we can also do Fresnel zone plate-like structures by means of ultra-precision diamond tooling. So this can then also be made in a mold that can then be used again as a shim in a replication process. So we can really make different combinations of the different processes that we have available to make particular components. Finally, the microfluidics. Of course, we can do very high accuracy optics, and we can therefore also do microfluidic channels and even combinations of microfluidics with integrated optical components, either by high precision milling, ultra precision diamond tooling to make the shim that can again then be used in a replication process to replicate the component into polymers, or in this case, the direct fabrication by femtosecond laser machining in glass is also a great possibility, because for the microfluidics channels, you typically don't need optical quality sidewalls. And so that's something that can already be done at this point. And again, we plan to further work on the process developments to decrease the surface roughness of the resulting structures by applying a fluid jet polishing process on those fabricated glass samples. That's what I wanted to say. So you have my contact information here, and feel free to also ask any questions that you have at this point in time, or to get in touch later on to discuss further the technical capabilities. Thank you very much for your attention.
Thank you very much, Jürgen. Is there any question now? If it is not, I would suggest, oh, sorry, Rasko.
Hello, Jürgen. Thank you for the presentation. On slide 11, you showed that with this down taper, you make a physical contact to an indium phosphide chip, for example. I'm curious, is there any damage to the facet? Is this process reproducible? Because indium phosphide is quite brittle material.
Yeah, of course, when doing the physical butt coupling, you don't want to come in with excessive force, and so you do a careful approach to the chip. And what you see is actually that when you, especially with a linear down taper, if you are in contact and you continue to apply some forward force on the fiber, what you would see is that the taper would start to flex. So since it's a polymer taper, it takes up most of the force applied to it. If you apply some further force, it will start to flex. If you then release the force, it will normally go back to its original situation. If you really push it too far, the taper will break, and then you have a plastic deformation. It will not come back to its original form. But then you really have to push pretty hard. So we haven't seen damage to the chip yet. And in case of the linear taper, it would take up the force that is excessively applied. In case of the nonlinear taper, because it's much shorter, it's a little bit more difficult for it to flex. So there you don't see really flexing, and you have to be a bit more careful. As well, for the microstructured taper, and there your contact surface on the chip is a little bit larger, so you probably also have a more distributed force application on the chip, which would probably just distribute the force a little bit better than in case of the very small end tip of the linear taper. So up to now, I would say no, we don't see too much damage, but of course, yeah, as you would do also with a lensed fiber, you approach under a microscope with some care. If you really bump into the chip, you would probably be able to cause some damage to some extent. Yes.
Understood. What if something in the writing process goes wrong and you want to rewrite the structure? Do you typically cleave the fiber, or can you just remove it?
Well, in many cases, because we apply some chemical processes to increase the adhesion, and you also have the base layer there. In the end, it's easier to just take another fiber than to try to get it off, because you cannot be 100% sure that you don't damage the fiber by trying to push it off, or there is no way to just dissolve the polymer. We haven't found a chemical etching solvent that would dissolve the structure. So typically what we would do is just take a new fiber and start over, because in the end you need to take out the fiber anyway. And reposition it afterwards again. So yeah, it's often easier to start with a new structure than trying to remove it from there.
Understood. Can I ask one more question?
For me, sure, yeah.
I worked with similar structures, photonic wire bonds from KIT. And when I worked with lasers, I observed that sometimes due to reflection, my laser output would change after writing such a structure. I'm curious, have you observed similar things due to reflections, and how high are the reflections at the interface?
There are, of course, some reflections at the interface, and up to now we haven't done too much testing with some index matching material in between the devices, because since you are aiming at a butt coupling connection, you could apply some index matching material in between the two to reduce these reflections. I would have to look back at the exact values of the return losses. I think in the papers they are mentioned over there. I don't have them at the top of my head, but they are what you typically would expect with Fresnel reflections on the end surfaces of these devices. And so you have about 1.52 refractive index of the polymer. So you can get an estimate of how much Fresnel reflection you would have on these end facets.
Understood. Thank you.
Welcome.
So there are no other questions at the moment. I would say thank you again, Jürgen, for this interesting presentation. And now we've got the chip and we've got the optical connection to the outside world. Now what is missing? The electrical connection and the packaging. And for that, I want to hand over to Donald Bihal from the Tyndall Institute. And I want to please you to start with your presentation. So Donald, you have to unmute your microphone first.
Okay, thank you, Dirk. Can you all see my screen there?
I can see your PowerPoint,
Yeah,
not the full screen. Oh, now we see the full screen, yes?
So my name is Donald Bihal, and I am the project manager for OIP in Tyndall, and I also the project manager for the PICs pilot line in Tyndall. What Tyndall has excelled in the last years in photonics packaging is we have been working very hard on getting to reduce the cost of the packages. But without further ado, what I want to explain is you've heard from Smart Photonics that they're talking about the foundries and the technologies used. And from Jürgen, you've heard about the micro optics. So Tyndall has been looking really at the assembly of packaging in the back end, and over time, what we have seen is that there is more and more overlap between the front end and the back end. And we are trying to bring in all the designs and standards to work. So we have a more easier approach to, rather than having to customize every single optimized package, that we can build from a series of building blocks. So integrated photonic packaging is just all the techniques that you've heard about using microfluidics, for example, for thermal management. We look at the active and passive optical connections. We look at the electrical connections. So this is basically, we're trying to connect the PIC that has been produced by the foundry to the outside world. So mainly we have 4 blocks in packaging technologies, which we the mechanical, the thermal, the electrical, and the optical. So what we're trying to face are some challenges. So as Nazarene mentioned in her presentation, PIC packaging is about 80% of the cost of a project in silicon photonics, and it comes down to about 60% with indium phosphide. So what we want to do is reduce these barriers of entry to the SMEs in the region. And we also want to be talking to our partners in the supply chain. So the limited availability of off-the-shelf products, that we can actually have more off-the-shelf solutions, that it will make it easier for us to build up a quick prototype, or basically if you're going to scale up the production, that you can take it to somebody like Photon First, and they can do hundreds of units for you quicker without having to customize a solution. So what we're bringing to the table in Tyndall would be offering validated scalable assembly processes and technologies, including the packaging of the PICs. We provide access to MPW runs and prototyping photonic solutions. And we also have a lot of access with other European pilot lines for scaling up the projects. So at the moment, OIP is looking at the prototype stage, but if some of you might be more advanced than prototyping and you want to scale up, we have access to other programs that we can help you with. So without further ado, this would be an example of a package. You can see the optical fiber coming in and talking to the integrated photonic circuit sitting on an interposer. And you can see that we have the electrical connections and other pieces of the package to connect and regulate the thermoelectrical properties of the package. So what we are offering in collaboration with our partner BUE will be a fiber-to-edge coupler, whether either a single fiber array or a single fiber, with a very limited pitch and a number of maximum of 12 channels at the moment, with a mole-field diameter of 3 to 10 microns. We're using a flip chip to connect electrical connections, and we're looking into microfluidics and other techniques for cooling down the packages. Now, these are validated building blocks. We know that they actually work. We can easily reproduce these processes, so we can then transfer it to our industrial partners in the pilot line to replicate. What we are given access is access to smart photonics to make the PICs for you. We also have the MPW runs across Europe that we can access, and we have a number of photonic solutions that we can base on prototyping. So Smart Photonics and TUE will be giving you the PIC in this industry funds, and BUB and Tyndall will be working on connecting that PIC that we got from Smart Photonics into a solution. Lastly, the offer that we give to our partners or SMEs coming through the voucher schemes, after they come through prototyping, if OIP can continue doing the project, we'll continue through OIP. But in case that you're going faster in the lines than we are able to support through OIP, Tyndall can give you access to a number of European pilot lines, which include a number of the members in this consortium. So we have PICSAP, who have the photonic packaging pilot line in Europe. We have JEPICs that are working with indium phosphide. We have ACFAs that give excellent support to SMEs with their projects in different technologies and developments. We have MEDFAB that deals with the medical devices, and it was only set up last year. And for silicon photonics, we can give access to Europractice. All these pilot lines are supported by Photonics 21, and they're part of the public-private partnerships of the Horizon 2020 program. So OIP is supporting the scalability of the fiber alignment processes within Tyndall and increasing the capacity of our flip chip technologies. In summary, what we're offering is to support you by giving you access to indium phosphide in PICs. We're talking to the world leaders when it comes to photonics packaging and optical connections with Tyndall, TUE, and BUE. And we also have access to the European pilot lines and ACFAS. So unless there are any questions, that would be from me.
So thank you, Donald. Are there any questions now? If not, I would say thank you again. Oh, there's say thank you again, Donald. Perhaps we've got questions and discussions after that. So after talking about the technology and the technical offers that we can do, now let us talk to another important topic, and that's the money. Because producing of chips is very expensive. So we would come now to our innovation support fund to help you to make it a little bit more easier or a little bit cheaper for you to use this. And I want to please Jürgen van Erps again to talk about and to present and to introduce our innovation support fund.
Yeah, thank you, Dirk. So once again, good morning. Full screen. Okay. So indeed, as mentioned also by Victor already this morning, we have an innovation support fund in place, which basically is aiming at SMEs in the Northwest Europe region. So if you have a particular PIC which you would like to take to a next step, so beyond proof of concept demonstration. So if you have already something available, but that you would like to scale up, then there is a possibility to apply to our call for vouchers, where you can receive up to 50 kilo euros of financial support by access to the pilot line. So the vouchers can cover the design verification to check compatibility of the design with our pilot line, as well as the manufacturing of the PICs, the external optics, and the packaging of those components. So the call has opened on the 22nd of January. We had a couple of webinars, including the one of today, and the call will be open until the 15th of April. So between now and then, you have time to submit an expression of interest. So there is a one-page document in which you can briefly describe your intention to apply to the call, and then we can already do an early eligibility check, and then you can, if agreed upon, you can submit a full application form. You will also have to sign a proxy NDA in due time, such that by the time the call closes, we can evaluate the proposals by the selection committee that has been put together within the network. And we expect to be able to announce the winners of the vouchers in the course of the month June of this year. So all of the information is also available on the website, and so you see the link there at the bottom. But I will briefly go through some of these documents that need to be filled out and the requirements to which you should adhere in order to be eligible to the voucher scheme. So first of all, you need to be an SME according to the European definition, and you need to be based in the Northwest Europe area as defined by the Interreg program. So the two links are mentioned here on the slides, so that you can have a look at the map and at the definition to be sure whether you comply or not. As mentioned, your technology readiness level should be 4 or higher, so you should have preferably a PIC design ready and preferably a validated prototype already. So we are mostly aiming at trying to upscale production, so to provide a series of devices rather than a proof of concept demonstrator. And next to this technical feasibility, you should also prove a business case. So you need to show that that your access to the pilot line and the scale-up result of the project will positively impact your business, which can be either through increased revenues or through the creation of new jobs. Of course, you should also comply with the de minimis criterion for state aid. These are a little bit more administrative, but yeah, I can provide some further information on that if required. And as mentioned, you should submit a fully completed application form, sign a proxy NDA, such that all of the members of the voucher selection committee can evaluate the proposal. And finally, it's also required that the voucher recipients agree to collaborate on documenting their use case. And so this is just to use these pilot cases as dissemination material to attract further users in the future after the first round of voucher projects have been finished. It is clearly indicated which information is to be made public in the application form. So as mentioned, the application procedure is consisting of 2 steps. So first, there is an expression of interest form, which should be filled out and sent to this voucher at OIP4NWE.EU email address. It's only containing some very general information, contact information, and a brief description of the project you intend to do. And in the second step, there is a full application, which is also quite limited in page numbers. So this should be submitted by the call closure on the 15th of April. And let's just browse through that in a little bit more detail. So you have, first of all, some company information. The asterisk here indicates the things that we would make public in the end for dissemination purposes. So company contact person, some general project information about application domains and so on. And then the project description, this is basically the technical side of things. So again, there is a short abstract which should describe in a couple of lines what the project is about in a way that it's presentable in for public purposes, and then you can go in a little bit more detail with information that is confidential and will stay within the evaluation committee. Context of the innovation proposal, some general description of the approach that you plan to follow, some major challenges or target specifications that you expect, and so this is some further detail on the technicalities. And then in part B of the application, we're looking at the impact on the company's business, as mentioned. Again, put on my laser pointer, that makes it maybe a bit clearer than my mouse. So there should be some information on the business aspects. So about the target markets, market validation, the route to market that is expected, your unique competitive advantage, and a brief business plan. And importantly, also your new business and EU jobs that you expect to be created from this project. And so in this table, you can fill out the expected new revenues in the 5 years following the completion of the project, or the additional number of full-time equivalent jobs that you plan to hire thanks to the results of the project. Once you have submitted your proposal, then the evaluation committee will evaluate it after the call closure, and it will be evaluated against the following criteria, which all have an associated weight assigned to them. So first of all, we will look at the innovative character of the project. And so is it really creating valuable know-how? Is the PIC key enabling element in the project? And then secondly, also related to this is the technical feasibility and the quality of the project plan. So is the project compatible with the pilot line? What is the current TRL level, and so on and so forth. But next to these technical aspects, and we will also look at the credibility and level of commitment of the company. So the level of financial commitment refers to the fact that 20% financial contribution is required from the SME until the maximum of 50K euro support. And of course, if the total project size would be larger than 50 kilo euros, then of course anything above the 50K should be fully funded by the SME. As well as some track record in bringing products to the market, successfully completing funded projects, and so on and so forth. The fourth aspect on which the evaluation will be based is the added value on the business case and the potential impact. As mentioned, that these are also important things to take into account and are directly related to the questions that are asked in the business plan part B of the proposal. Yeah? Each of these criteria should be scored at least should score at least 2.5 out of 5, and the total score of the 4 in total should be at least 20 out of 30 to be eligible for the vouchers. And next to those aspects, the selection committee might also take into account geographical distribution across the Northwest Europe region. That's in case we have many applications, and that we need to also ensure some geographical distribution, as well as distribution over different application sectors. And we have to avoid that, if possible, that all 7 vouchers are from for example, the telecom application market. All right. So all in all, for more information, you can visit the website or send an email to voucher@OIP4NWE.eu, and we will get in touch and provide you with any answer to the questions you may have about the voucher scheme. And of course, I'm also willing to answer any questions you may have at this point. Thank you very much for your attention.
So thank you very much, Jürgen, for introducing this Innovation Support Fund. Are there any questions from your side? For that instrument? If not, let me start with the first question. Jürgen, if I've got only up to now an idea, not a PIC design or something else, and you've mentioned the expression of interest. So can I come to you and you say, I've got an idea, is it possible to do this?
Yes,
You're the one
absolutely.
to say?
Yes, absolutely. So feel free to fill out the expression of interest and give a brief description of the current status of your PIC idea. Of course, if it's very early stage in the low TRL levels, then you will not be able to apply to the vouchers here. But many of the partners involved in the project are also involved in other instruments that are available. Donald mentioned the pilot lines, the innovation support through ActFast, for example. We are also linked to the Photon Hub Europe initiative that will be launched or that has launched last month. So even if the outcome is that you are not eligible for a voucher here, we will be able to put you in contact with the right platform. So if it's very early stage, very low TRL level, for example, you would be forwarded to ActFast, where you will have also some funding opportunities over there. And so feel free to fill it out, even if you upfront know that it's borderline. We will be able to get you in touch with the right people to make sure that you're pointed towards the right platform for further support.
Okay, thank you. So you're the one-stop shop for the PIC pilot lines in indium phosphide or perhaps in other technologies for that. Yes, Donald?
I just wanted to add that to Jürgen's comment regarding the applications. It will help OIP to have these applications that may not qualify to know what markets or areas are upcoming where we can base our future research or improvements. So it is important to know whether you are if you're not in the communications market, maybe you're looking into agri-food or mobility and transportation. We need to know where the interest is so we can focus our resources to improve these areas.
Good point. Yeah. So it's definitely also of interest for us to know what you're thinking about and what your ideas are. Definitely submit an expression of interest as if you have something in mind which you would like to further explore.
Thank you, Donald. Another question? Or you're better thinking about at the moment, what can you do? What can we offer to you, to all the participants, to all the fabulous companies and whoever is interested in such a PIC?
Maybe it's also good commenting, Jürgen, could you clarify if this is a single opportunity or there will be others after this call?
Yes, so as mentioned, we have in principle 7 vouchers available for distribution. Of course, if we don't have a sufficient amount of good quality applications in this round, we will launch a second call for vouchers later on, such that there are, of course, also further opportunities potentially. If the 7 vouchers are distributed in this first round, then we don't open a second call. But if not, we will open a second call later on.
So thank you, Jürgen. So feel free, you've heard, you've got at the moment 7, but the chance is very high for you. So it's not like an EU and Horizon 2020 or an Horizon Europe project where you've got a success rate of a few percent only or 1-digit percentage. So I think, or I hope that you're not working or you don't write the expression of interest, or you write your proposal and you need time for that to write it down and then say, okay, you've got no chance to do this to be successful there. So I think you've got a real chance to get such a chip from us and to get a voucher for our support fund. If there are no other questions at the moment, I can only say thank you very much for participation. To all of you, we will send the slides from today to all of you. They are published or will be published at our webinar website at OIP4NWE.eu to have it there. And the only question is, so before we close this webinar, someone has got the chance to say a last word or to say or to ask a last question for today. If it is not.
Oh, well, just thank you to the attendees. And I want to mention that if everybody has questions later on, well, just feel free to reach the main contacts of the consortium, and we'll be happy to clarify your questions or to help you spread the word in your network. Well, okay, that's it. Thank you, everyone.
Yep. So thank you for participating.
Have a good day.
Have a good day.
Bye-bye.
Thank you.
Bye-bye.
Thank you. Bye-bye.